Hello, my name is Chad Varney and I'm an application engineer here at Ally PLM Solutions, and I'd like to welcome you to another session of NX CAM Lunch Bytes. Today we're going to look at repair work in NX CAM. We have several of you on the line with us today, so you'll be in listen-only mode for this session. If you have any questions after the session, you can email them to me at chad.varney@allyplm.com. I want to remind you that we have all of our Lunch Bytes replays available on our website, and you can check those out at www.allyplm.com. We also have a section where you can give us your suggestions for future Lunch Bytes topics. So today we're going to look at several ways to use NX CAM to do repair work. Repair work could consist of design changes, reconditioning a part, adjusting part dimensions, or recutting damaged areas of a part. There are many different options in NX CAM that can help us create quick and efficient toolpaths for specific areas of a part or an assembly. As we look at today's agenda, we'll see several examples of how to utilize NX CAM for making changes or doing repair work. We're going to look at some tools in NX CAM that help us prepare for a repair or design change. Then we're going to look at how to properly set up our blank geometry, and also some ways to specify our cutting area. And lastly, we'll look at some ways to trim a toolpath. So we're going to look at the first part, and we're going to talk about inspecting damage from a tool holder collision. This part has a solid profile 3D operation using a 30mm cutter with a length of 105 millimeters. However, the part was ran out on the machine with a cutter that was only 95 millimeters out of the holder, which caused the holder to gouge the part. The process for the repair will be to weld the gouged area and then remachine it back to the correct shape. So the first thing we need to do is decide how much weld will need to be placed on the part. To do this, we'll change the length of the cutter to 95 millimeters inside of NX to simulate what actually happened out on the machine. So as you can see, we have our solid profile 3D operation. And I'll go into the operation and take a look at the length of the tool. Notice the length of the tool is set to 105 millimeters. We'll go into Verify and do our collision check and play this through. Notice at 105 millimeters, the tool or the holder doesn't collide with the part. So as I mentioned, we're going to imagine that out on the machine, the tool was actually ran only 95 millimeters out of the holder. And again, this would cause a collision. So what we want to do is find out exactly how much material has been removed during this collision. So to simulate that, we're going to go into our tool parameter settings and adjust the length to 95. And then regenerate the operation and go into Verify. And I'm going to go ahead and step this through without collision check turned on, just to visually look and see what's happening to the holder and the part. As we can see there, the holder actually starts to collide into the part. and as it works its way around, we notice the rest of the toolpath is safe. So we can do this again with collision checking turned on, and now we see the area in red indicates that the tool or the holder has collided with the part. So again, we need to estimate about how much material was removed from this area by the tool holder so that we can tell the welding department how much weld needs to be placed on this part. To do that, we'll simulate the tool in the position where the holder collided with the part, and then we'll use the measure distance command in NX. I'm going to do a projected distance in the Z-axis, and I want to measure from the face of the holder to an edge on the part. And we notice that we have about 3.9 millimeters. This means that's what's been removed or gouged on the part. So now we could tell the welding department we need about 4 millimeters of weld in order to recut this gouged area. And now we're going to take a look at an example of a design change. We're going to open up a revised version of the part and then determine what will need to be done to complete the design change. As you can see here, we have a couple of boss shapes that need to be added to the current part. So what I'm going to do is just simply add that revised part into this assembly. I'm going to add in the revision A. And now we're comparing the two models, and we can see that this boss shape on the top and then down in this detail area are added. The process for this repair is going to be welding as well, so we're going to weld up those two areas and then remachine those shapes back to the revised size and shape. In order to do this, one of the things that we can do in NX CAM is we can use an engraving operation to lay out the areas for the design change. This will allow the welding department accurate information so that they can apply the welding areas according to the design change. So the first thing we'll do to create a engraving operation is first we're going to use the wave geometry linker, and I'm going to use the composite curve and select the curves around each of the design change areas. And what this is going to do is actually create curves inside of the original design model, not the revised design model. This is going to be in the original design model. And also you'll notice the setting that I have over here in the geometry linker dialog. I have associative turned on, which means if the size or shape of these two design changes change, it will update these curves so they will remain associative to the revised model. Now I'm going to just simply hide that revised version, and now what I'm left with is our design model along with the 3D curves, again associative linked curves, that represent the welding area. Now I can do a contour area operation with a small ball cutter. And I'm going to use the curve point drive method. And I'm simply going to select the curves that I have linked with the original or with the revised part. And I'm going to add a new set, since these are two different sets of curves. And go ahead and generate the operation. Take a look at this in verification. So now we've basically drove our toolpath according to the outer lines of the two design changes. And I can apply a negative stock amount so that this will actually engrave the part slightly. So again, we will engrave these outlined areas so that the welding department knows the size and shape and location of the two design changes. Alright, now we're going to take another look at an example of another type of design change, but this time we're going to use a different method to complete the design change. As you can see here, the design change is highlighted in green, and we're going to assume that the part has already been cut down to the original shape, and we're going to install an insert block to add the material needed for the design change. And as you can see here, the insert block has already been modeled and it's shown in gray. So for this example, we're going to talk about setting up our blank geometry. Most times when we define blank geometry, it's usually maybe a bounding block, part outline, or maybe another solid model such as a casting or something like that. In this example, I'm going to use the insert block as my blank geometry. This insert could be a separate body inside of this original part file, or it could be a separate component in an assembly. So I'm going to define my workpiece. I'm going to first specify the part, and next I'm going to specify the blank. Again, I'm going to use the insert block as the blank, and you'll see the advantage of this after I generate a toolpath. And I'm going to go ahead and create a cavity mill operation. Alright, since cavity mill uses the IPW, in-process workpiece, we don't have any excessive cutting or air cutting. This is because we defined the blank geometry correctly as the insert block, which is the actual material that we're starting out with. So this is a good way to limit your tool paths and reduce air cutting or excessive cuts by defining your blank geometry as the actual material that you're going to be cutting. And we're now going to look at another example of setting up your blank geometry. In this part, we're going to assume that the two contoured walls are slightly out of spec. So the process for the repair is going to be to weld the two walls and then recut them back to the correct size. As you can see, the areas in green represent the welded area. So we're going to assume that these two walls are out of spec, and the green represents how much weld is currently on the part. We're going to assume that everything else has been finished, so all we need to do is cut these two areas. Well, when setting up our blank geometry, we can actually set both areas up as our blank geometry. So I'm going to specify the part and then specify our blank, and I am able to pick both or multiple solid bodies for our blank geometry. Now I'm going to create a cavity mill operation just like we did in the previous part. So notice our cutting area is contained inside of the blank geometry. So we don't have excessive cutting in between the two areas that we need to cut. We're only cutting inside of the areas that need to be repaired. You can imagine if this was a much bigger area between here, that would save a lot of cutting time. So again, blank geometry is very important in setting that up correctly, and I want to make you aware that you can set up multiple solid bodies as your blank geometry. Now we're going to talk about how to easily cut specific areas of a part like this one that has many different faces. We're going to assume that we only need to machine 2 of the 8 contoured shapes on this part. We'll imagine that the 2 areas were found to be out of spec and will be welded up and remachined. However, I need to create multiple operations for each shape. Since I don't want to pick each face in each of the 2 areas every time I create an operation, I'm going to create mill area geometry. The workpiece and blank have already been specified in this part. So now I'm going to add an additional piece of geometry called mill area that will reside underneath of our workpiece. And I'm going to rename this repair area. And for the repair area, I'm going to simply specify the 2 areas that I want to cut. Notice I'm just window selecting the faces. Now that my geometry is set up, now I can create rough, semi-finish, and finished toolpaths. I'm going to create a Z-level operation. Notice I'm going to use repair area as my geometry. So as I create this first rough operation, you'll notice it's contained in the two areas that I've set up in the repair area geometry group. So now I can go ahead and continue creating my semi-finish and then finish operation. Alright, there's my semi-finish operation. And then lastly, I'll create a finish operation. Again, I do not have to pick each area that I want to cut. I only had to pick the faces one time and then set those up as a geometry group. You can also imagine that if I needed additional tool paths in these areas, like let's say for the corners, again, I would only need to pick these areas one time. Okay, and the last thing that we're going to look at is trimming toolpaths. We're going to actually look at trimming a toolpath as we're rotated in a certain view. As you can see in this part, I have a contour area operation already generated. However, notice how the toolpath goes down in the deep contour area. That may be an area that I want to cut with a different tool, or there could possibly be a design change in that area, or I may want to just cut that area at a different time, a later time. Well, I'm going to edit the toolpath and trim out that section that I don't want to cut. So in order to see this a little bit better, I'm going to change my shading to a static wireframe. That way I can see the toolpath through the part. There are several ways that we can trim a toolpath. One of the ways is specify trim boundaries inside the operation itself. What we're going to look at now is editing the toolpath and then going into the trim option. Notice there are several ways that you can use the trim option. You have planes, align in a view, boundaries. What we're going to use is section in view. So when I start trimming this, it will be trimming in the view that I'm currently in. So for example, if I have the part rotated in this direction, this is the area that I'm going to be cut. It's going to be normal to the view that I'm currently in. So what I want to do is rotate the part around. I'm hitting F8 on my keyboard to orient the part to the nearest view. And now I'm able to trim while I'm in this view. So I actually want to trim along this line here to get it out of this deep area. Instead of window, I'm going to use the lasso. And trim that section out of the toolpath. Again, there are different ways to trim, but I just like to use that view option sometimes, because you can get a better idea of exactly what you're trimming and get a better visual look at what you're actually trimming. So now notice we've cut out that unwanted area, but we've remained, our original toolpath has remained intact. Well, that's all the time we have for this session of NX CAM Lunch Bytes. Hope you're able to learn a few things about doing repair work using NX CAM. If you have any questions about today's Lunch Bytes topics, you can email those to me at chad.varney@allyplm.com. I also want to encourage you to go to our website at www.allyplm.com and check out our current NX training classes. We offer a wide variety of NX CAD and CAM training options, including our new NX CAM Advanced Techniques class and our new Advanced Techniques for NX Designers class. Our training classes can be taught here in our Cincinnati, Ohio location, online, or on-site at your facility. Again, I want to thank you for joining us. Hope you have a great day.